Okay, here we're going to look at an example of the integral test to see if something converges. I'll just quickly run you through it. So suppose f is a continuous positive decreasing function on the interval from 1 to infinity. So it includes 1, but it obviously doesn't include infinity. Let an equal f, so some function of n. An is a sequence, where n is a positive integer, the natural domain of a sequence, such that all of the terms in an in the sequence are positive. So it says if we turn the sequence into a function of x, so if the improper integral between 1 and infinity of f of x is convergent, then the infinite series of an is also convergent. If the improper integral is divergent, then the infinite series is divergent as well. So this particular test is really handy if you've got something that's fairly easy to integrate. So it's really good to be really strong on your integration. And then we look at it and say, well, if we could integrate it nicely, then it's a good way to do it. It might not be the only way. This one, for example, a comparison test would potentially be an easier way to do it, comparing to 1 over n squared. But I'm just going to show you how you can do it with the integral test as well. So test the infinite series from n equals 1 to infinity of 1 over n squared plus 1 for convergence, right? So if we look at that, imagine if we change this into the integral from 1 to infinity of 1 over x squared plus 1 with respect to x. So if we turned it into a function of x, is that something we could integrate reasonably easy, and would it converge? So I just got an extract from the formula sheet. So standard integrals, now the actual standard integral bit isn't as handy as if you just look at the standard derivative. So this is just taken directly from the formula sheet. It's always worth a look, because it would save you doing some kind of u substitution that might end up being really, really difficult. But this is just one of the standard integrals. So the integral bit itself is more general for some general a, but if we look at the actual standard derivative, well, this is really handy. It tells us that if f of x equals arctan x, then f dash x is exactly what we've got. So if we go backwards, that is telling us that the integral with respect to x of 1 over 1 plus x squared is just arctan x. So that's actually going to be quite a nice result. So now this equals, we do need to do the improper integrals properly. So we need to say, well, this is the lim as b approaches infinity of the integral between 1 and b of 1 over x squared plus 1 dx. Okay? So we now know this is going to be arctan x. We don't need to worry about the plus c because it is a definite integral. So equals the lim as b approaches infinity of arctan x. And we need to evaluate that at the upper limit of b and the lower limit of 1. Right, so that is going to be the limit as b approaches infinity for arctan b minus arctan 1. Arctan b minus arctan 1. Okay, so you might look at that and think that that's quite tricky, but actually if we draw a unit circle, it becomes really easy. So if we just draw a nice unit circle, so we need to find basic arctan infinity, so as in an angle such that tan of the angle is getting near to infinity. So basically an angle such that when we approach it, tan of the angle is approaching positive infinity. Now remember, the unit circle, tan is the gradient in the unit circle. So if we can consider the gradient, you're looking for, well, when do we get an infinite gradient? It's when you have a vertical line. So if we are kind of up here and going this way, you can see that the gradient is approaching infinity, so tan of the angle is approaching infinity. The angle itself is approaching pi by 2, 90 degrees. So our first one is pi by 2. Arctan 1, well, you should know that. So tan of what angle equals 1? And it is this angle here, so that is pi by 4. Okay, so now we have equals pi by 2 minus pi by 4 equals 2 pi by 4 minus 1 pi by 4, which just leaves us pi by 4. Now, it doesn't actually matter what it converges to. Remember what we're doing. We're using the integral test to see if the series converge or not. So if we just go back up, so now we know that the integral converges. That is enough to tell us that the infinite series also converges. So we can just write that as integral, the improper integral between infinity and 1 of 1 over 1 plus x squared dx converges. As that converges, then the infinite series from n equals 1 to infinity of 1 over 1 plus n squared converges as well. The reason being the integral test.